So any question on what we have covered by way of helping you with the problem last time, the boundary condition, do you understand that? You said in the problem statement that on the free surface, which is when y equal to h, there's no shear, and it resulted in this conclusion, which is important later on. Do you understand what's meant by the boundary conditions? And that the wall at y equal to 0, low slip, always resulted in velocity both in x and y, always equal to 0. Okay? And then move on to continuity. The only piece that I left and I didn't tell you, and I hope you see that yourself, is that when I apply continuity and some of the terms drop out, I have now remaining the velocity v to be determined. What is v equal to? Anyone? 0. How do you know? It is 0. How do you know? Say that again? No, that's not how you conclude it. You have to use the boundary conditions to come to that conclusion. Let's do that integration. If this is what we concluded from continuity, what is the next step we can do? To integrate, right? And that tells you, when you integrate, that the y is a constant, plus a constant, right? What is this constant? How do you know how to determine this constant? You use the boundary condition right here, which tells you at y equal to 0, the v must also be, or rather, at y equal to 0, the v velocity is 0, so the constant then must be 0. So v is 0 everywhere. Does that make sense? I'm sorry?
You just integrate it to 0, and you get a constant, not, there should be no y term.
I can't hear you, I'm sorry.
Like, it should just be v equals a constant, because there shouldn't be a y term. When you integrate it,
V equal to constant, yes, I'm sorry, that's why I'm confused, yep, thank you. Yes, yeah, thank you. So for the entire remaining problem, v being 0 is very important to further simplify the problem. And that's because in this fixed momentum equation, last time we have canceled a lot of the terms. And from here, we conclude the last term is also 0. Right? Do I have to go through again how our other terms disappear? Which we did last lecture. So from the x momentum equation, what remains is simply this term. And that's where you're supposed to leave the answer. Where did I get g sine theta? Anyone? It's my gravity in the direction parallel to the plate. Any question on this? That's all I'm asking for. Yes?
So from a bigger picture view, is Navier-Stokes for laminar, turbulent, or both?
Okay, let me repeat that question because it's very important. Everything we have done so far for the Navier-Stokes equation is only good for laminar flow. Anytime you have turbulence, an added velocity, an unsteady term has to be flow in, and all of this is irrelevant.
And that's what you were talking about last class.
That's last lecture, I keep trying to emphasize that all we are doing is just laminar flow only. Correct. And they're very limited, but they are very illustrative to help you at least have a handle on this Navier-Stokes equation. But in real world application, I'm sorry to say this doesn't apply, because most of the flow is turbulent, right? But this helps you to understand a very good basic fundamental that when you go out to the real world and you use some computational software to look at problems, turbulent will be included, and you have to know something called turbulent modeling, and that changes all the dynamics, okay? But this is more basic and building block that is important for you to understand and appreciate. I will come back to this momentarily, but right now I want to look at the second part of the problem, which is the Y momentum equation, and hope that many of you were able to do this based on our discussion in the lecture. So that's the part I want to go over because that wasn't covered in my lecture last time. And at the end of that, I think you find some very striking and interesting conclusion. So help me to simplify this Navier-Stokes equation in the Y direction. What is G sub Y? Anyone? It's G cosine theta. Based on that triangle that I draw. Any question on that? Yes?
Negative? Because it's on the Y plot.
Yes, thank you. It is negative. Thank you. Anything else? Everyone understand why it's negative? Okay, what's the next step? I cannot touch dp dy, nothing is said about the pressure here, so I have to leave it alone. What about this term? Everything, if you see the fact that V is 0, everything here basically disappears. So what left? What left is rho G cosine theta. Question on that? Question on that? Yes?
Can you get rid of the viscosity term, the dV dy squared?
Here?
Yeah, that one.
Can I get rid of it?
Yeah.
If V is 0 everywhere,
Okay.
then you can.
And it's steady temperature.
Right. Correct. Very good point, very good question. But if V is everywhere, there's no second derivative. But when you look at this equation, what may remind you of, if you integrate this resembles the form of P equal to rho G H. Right? So you integrate that, the dy become just the height. The cosine theta is there because the plate is inclined. So it become, when all said and done, hydrostatic pressure. Not surprisingly. Now, a further step, and it's interesting, but not requiring a problem statement, is that it turns out I can take this equation and do what to it? Anyone? As shown, I don't know any of you have actually taken the time to do that. I can use this equation in differential form, second order equation, to solve for the function of the velocity s of y. And then apply the boundary condition, I will be able to obtain the u velocity distribution within that thin layer of water. And let me just walk you through that because it's interesting. But again, I emphasize it's not required in the problem statement. So if I start with just a little bit of algebraic rearrangement, I'm proposing to integrate this equation twice. First time, resulting in an integration constant, and then another integration, give me now two constancies of integration. Okay? This is, although academic because it's laminar, but it's still very insightful and interesting. Tell me if you take these two steps, and I don't think any of you have done it, what is there to determine what C1 and C2 is? Boundary condition. Boundary condition. If you do that, which I won't go through the math, because it's just algebra, I will apply boundary condition 1, which is at height h, no shear, resulting in this equation, that the velocity gradient is 0. Boundary condition 2 is at the wall where u is 0. Two equation, two unknown, C1 and C2. And the algebra is something you can work on, and I think it's worth for you to give it a try. So when I'm done and settled, what I have is, as a function of the velocity parallel to the plate as a function of y, the height from the plate is given by this equation. It's a parabolic velocity distribution of that thin layer of water along that plate. Sketch it. It's a parabola with zero gradient or zero slope right at the surface. Yes?
Should there be 1/2 when you're integrating?
Yes. Oh boy. You're right. Yes. So I'm missing a 1/2 right here. Thank you for pointing that out. I'm missing a 1/2 in the equation. Yeah, thank you. So as though as it's academic, but this formed the basis of what we call computational fluid dynamics, which I ran out of time in this lecture. I will come back to that at the last lecture, at the ending lecture of the semester, to show you how all this can tie in and make a career for you when you go work in industry. All right, for the remaining 5 minutes, let me set you up for the last homework. problem. But prior to that, any question on what we have done for this? For this boundary layer problem? No? Okay. So problem 679. I have two plates moving in opposite direction. And the gap between them is B. Gravity is not to be neglected. And you are told the plate is infinite. Parallel plate. And it's two-dimensional. Every cut in the board and out of the board is the same, and it's steady, and it's incompressible. And it's laminar. Always, everything we do with is laminar. Take the continuity and momentum equation, which I will write out for you, and tell us what you can learn from this overview. So here's continuity. And here's x momentum. That's all required, x momentum. So I'll give you some hints on how to simplify the equation and leave you with the rest of the problem. And Mike will pose a solution to all the problem as we always do, so you can check yourself to see if you get what is intended. So I have about 2 minutes left to give you the appropriate hints. It's not obvious, but why I have an infinite plates like this, two-dimensional, it implies that the flow is fully developed. And that conclusion comes from the fact that the plate is infinitely big towards the wall in the window and towards the wall at the door. And as such, they have to be fully developed. There's no other choice. And that changed the dynamic of the problem as to what you can simplify a lot. For example, fully developed means that everything in the direction of x, in terms of the gradient or the derivative, is always 0. What can you tell me the simplification for the continuity equation? What about this time?
Say the other.
Same, 0. And then apply the boundary condition. I'd like you to figure out what is V equal to. It's the same as what we did with the inclined plate problem. So I'll give you the answer. It's going to be 0, but you show me how. Show me how. Okay, one last piece which I almost forgot that is fatal is you're given in the problem statement. This is also fully developed. It's such that there's no pressure gradient, dp dx, and that's actually in the problem statement. dp dx is also 0. So that go away. I will ask you to conclude what happened to the g sub x. Fully developed. Second derivative of the velocity in the x direction is also 0. How do you steady? How do you steady assumption? This term is 0, and this last term from fully developed is also 0. Okay? Questions? The last term here, you have to, this part A, to determine how to simplify that. And with that, the equation becomes very simple, stripped down, and you integrate it, and you should be able to get the answer. Okay? Very good, thank you.